Behind a cabin, somewhere in the southern mountains, there is a wooden box on legs, tilted with a trough underneath it. A woman fills it with ash carried out of the fireplace all winter, and she pours rainwater over the top. Nothing happens for a while. Then a dark liquid begins to run out of the bottom into the trough, and she catches it. To test it, she drops in a feather, or an egg, or a potato, and reads the answer off what happens. If it eats the feather, it is ready. If the egg rides high, it is ready. If it sinks, she runs the water back through the ash and waits. Then she takes that liquid and boils it with the grease she has been saving for months. The trimmings, the rinds, the fat skimmed off the top of everything cooked since autumn, and stirs it for hours until the whole thing changes into something else. She has no word for what she is doing. Nobody in that county does. The word is saponification, and it will not be explained by a chemist until the 1820s. What she has just built is a surfactant, the same class of molecule that is in every bottle under your sink right now. That is the forgotten method, and the first half of this video is going to show you that it works, and why, and that the chemistry is not a folk approximation of modern cleaning, but the actual thing itself. The second half is where it gets more interesting, because the title's claim breaks in one specific place, and the man who proved where it breaks did it in a maternity ward in Vienna in 1847, and paid for it with his career and eventually his life. There is also a modern version of this misunderstanding that sends thousands of people to poison control every year, and it is committed almost entirely by people who believe they are cleaning the old-fashioned way. Start with the box, because the box is a chemical extraction plant, and nobody who built one would have used those words. Wood ash contains, among other things, water-soluble alkaline salts. Pour water through it, and those salts dissolve, and come out the bottom in solution. That is all leaching is. And the detail that mattered, which the women running these hoppers knew perfectly well without knowing why, is that hardwood ash is better. Hardwood ash carries more potassium by weight than softwood ash. So oak and hickory ash made stronger lye than pine, and a household saved its hardwood ashes deliberately. Rainwater was preferred too, and that is not sentimentality. Rainwater is soft, it carries almost no dissolved calcium or magnesium, and hard well water interferes with everything downstream in this process. Now the correction, because the popular version of this story is wrong in a way that matters. What comes out of a wood ash hopper is generally not the lye sold in a bottle today. Modern lye is sodium hydroxide or potassium hydroxide. What ash leaching produces is mostly potash, potassium carbonate, with some sodium carbonate and a scatter of calcium salts and other dissolved minerals riding along. It is alkaline at something around pH 11, and it is considerably weaker than the caustic hydroxides. Soap-making manuals written in the 1700s and 1800s are explicit about this, even though a great many modern tutorials are not. So how did anyone get a strong enough alkali? By adding slaked lime. Calcium hydroxide, stirred into the potassium carbonate solution, drives a reaction that produces potassium hydroxide and leaves calcium carbonate to fall out of the liquid as a white sludge. That is a genuine causticizing step. It is centuries old, and it is the difference between a wash water and a soap lye. Which brings us to the tests, and they deserve respect. The floating egg, the floating potato, the feather that dissolves. Every one of those is a crude titration, a way of measuring concentration with no instrument at all. An egg rides higher in a denser solution. How much of it breaks the surface is a proxy for how much salt is dissolved in the water. A feather is keratin, and a solution strong enough to visibly degrade it in a few minutes is a solution strong enough to saponify fat. She had no pH scale, no hydrometer, no balance. She had a repeatable physical signal that tracked the number she needed, and she had been shown how to read it by somebody who had been shown before her. And the reading had to be redone every single batch, because the strength of the lye depended on which trees had been burned, how completely they had burned, how long the ash had sat, and how wet the weather had been. There was no such thing as a standard batch. There was a second reason the hopper sat where it did. Ash accumulated in that fireplace, whether anybody wanted it or not. A household burning wood for cooking, and heat produced it constantly, and it had to go somewhere. The soap operation was, in that sense, a waste stream being converted into a product, which is the same logic running through everything else in that yard. The fat came off the top of the cooking pot, the ash came out of the fire, and neither had cost anybody a penny. One thing has to be said plainly, because this is not a tutorial and nobody should treat it as one. Concentrated lye is severely caustic. It causes deep chemical burns on contact and blinds people who splash it in their eyes. The women doing this were working with an unmeasured, variable strength alkali over an open fire, and burns were an ordinary hazard of the job. Now the reaction itself, which is one of the oldest pieces of applied chemistry humans possess. Fats boiled with plant ashes to make a cleansing paste show up in Babylon around 2800 BC, used for washing wool and cloth. Here is what happens in that kettle. Animal fat is a triglyceride, 3 fatty acid chains hung off a glycerol backbone. The hydroxide ions in the lye attack the bonds holding those chains on. The bonds break. The freed fatty acids combine with the metal in the alkali to form a salt, and the glycerol comes loose as a separate product. That salt is soap. The glycerol is glycerin, and in a mountain household, it stayed right there in the mixture rather than being extracted and sold off, which is part of why homemade soap feels different on the skin from a commercial bar. Commercial producers pull the glycerin out because it is worth money elsewhere. And now the detail that explains the single most common complaint about mountain soap. The metal matters. Sodium soaps are hard. They set into firm bars. Potassium soaps are soft and stay as a paste or a jelly. Ash lye is predominantly potassium. So the soap that came out of the great majority of these kettles was not a bar at all. It was a soft brown jelly, kept in a crock, scooped out with a hand or a paddle. That is not a failed batch. That is what the chemistry produces from a wood fire. And there was a workaround, and it is remarkable. If you salt the boiling soap with ordinary table salt, sodium chloride, the potassium and sodium swap places, and the soft potassium soap converts into hard sodium soap, which then floats up and can be lifted off. It is called salting out, and mountain and medieval soap makers both did it as a matter of routine. Consider what that means. They were performing an ion exchange reaction, deliberately, reliably, for a known and repeatable result. Several generations before anyone on Earth used the word ion. Nobody in that yard could have told you a single thing about what was happening. Every one of them could do it. The industrial history then arrives in 3 steps, and it explains why the hopper disappeared. In 1791, the French chemist Nicolas Leblanc patented a process for making soda ash from common salt, which for the first time made a reliable sodium alkali available in quantity. In the 1820s, another French chemist, Eugène Chevreul, worked out what saponification actually was, meaning the reaction had been running in kitchens for 4,000 years before anybody could describe it. And in the early 1900s, dry sodium hydroxide became commercially available to ordinary households. That last one is the moment the ash hopper died, and the reason should be noted carefully by anybody romanticizing this. Women who had been leaching ash all their lives switched to store-bought lye almost immediately. Not because they were seduced by advertising, because a can of measured, consistent, known-strength alkali removes the single worst variable in the entire process, and they had been fighting that variable batch after batch for their whole lives. The first store-bought chemical they were offered, they took. So does the old method work? Yes, and the reason is worth understanding, because it is the reason the title is half right. A soap molecule has two ends that want opposite things. One end is hydrophilic. It is attracted to water. The other end is a long hydrophobic hydrocarbon tail that repels water and is attracted to oils and fats. That split personality is the whole trick, and it does three things at once. First, those molecules crowd to the boundary between water and everything else, and lower the surface tension, which is why soapy water wets a surface instead of beading up on it. Second, the tails burrow into grease, dirt, and the fatty envelopes of a great many microbes, prizing them off the surface they are stuck to. Third, once enough molecules have surrounded a particle of grime, they close around it into a sphere called a micelle. Tails inward, holding the dirt, water-loving heads outward. That micelle is now compatible with water. It rinses down the drain, which means a bar of homemade lye soap and a bottle of modern dish liquid are not two different technologies. They are the same mechanism. Modern detergents are synthetic surfactants rather than fatty acid salts, and they were developed for a specific reason. Soap reacts with the calcium and magnesium in hard water and precipitates as scum, and synthetic detergents do not. But the physics of lifting and encapsulating is identical. And soap was never the whole system. That is the part most people miss, and it is the real answer this video has been building toward. A mountain household ran 5 different cleaning technologies, and each one attacked a different problem. Alkali in the soap for grease and organic soil, acid in vinegar for the opposite category, the mineral deposits, the scale, the hard water film that alkali does nothing about. Abrasion, sand, wood ash used dry, salt, corn cobs, a stiff brush, for whatever was physically stuck and would not lift chemically at all. Heat. Laundry was boiled in a kettle in the yard, and boiling does something soap cannot. It destroys organisms outright. And ultraviolet light. Wet washing spread on grass in the sun was not a quaint way to dry it. Sunlight bleaches organic stains, and UV genuinely damages microorganisms, and everybody in that yard knew that sun-drying made linen whiter and smell better. 5 tools, 5 failure modes, deployed separately and on purpose. And there were sub-specializations inside that. Salt was used dry as a mild abrasive that would not scratch, and wet as a stain treatment. Wood ash itself, used straight rather than leached, is a fine alkaline scouring powder, and it is what cleans the cast iron and the hearth. Sand went on floors, scattered, scrubbed with a stiff broom, and swept out carrying the dirt with it. Which is why old floorboards from working kitchens are worn in a particular way. Corn cobs, lye water, boiling water, a brick. None of it was bought. Now compare that to the modern arrangement, where a household buys one bottle labelled multi-surface and expects it to handle grease, limescale, stuck-on soil, disinfection and odour simultaneously. That is the strongest version of this video's title, and it is a fair one. Not that the chemicals are unnecessary, but that a person who understands 5 categories of problem and matches a cheap tool to each one will outperform a person spraying a single expensive product at all 5. And now the place where the claim breaks, and it breaks hard. In 1846, a Hungarian obstetrician named Ignaz Semmelweis took a post at the Vienna General Hospital and began looking at something everybody there had noticed and nobody had explained. The hospital ran 2 maternity clinics. The first was staffed by doctors and medical students who came to the delivery room from the autopsy theatre. The second was run by midwives who had no contact with cadavers. Women died of puerperal fever, childbed fever, in both. But they died in the doctor's clinic at several times the rate. Mortality in the first clinic reached 18.3% in April of 1847. Women knew the numbers. Some of them begged to be admitted to the midwives' ward, and some gave birth in the street rather than go into the first clinic at all. The accepted explanation was miasma, bad air. Semmelweis spent months eliminating variables like a man running an experiment, which is essentially what he was doing. He moved the beds, he changed the ventilation, he altered the route the priest walked when delivering last rites. Nothing moved the numbers. Then his colleague, Jakob Kolechka, cut his finger during an autopsy and died of something that looked exactly like childbed fever. And Semmelweis had his answer. The students were carrying something out of the dissection room in their hands. Here is the detail that matters for this video. He did not tell them to wash with soap. They already washed with soap. Soap and water was ordinary practice, and it was not working. He ordered them to scrub in a basin of chlorinated lime solution, a chlorine disinfectant, before every examination. Mortality in his clinic fell from around 18% in April to 2.2% by June, with similar figures through July and August. Later, at St. Rochus in Pest, he installed the same chlorine routine and drove the rate down again. It is worth pausing on how strange that result was at the time. Semmelweis had produced one of the largest reductions in mortality ever achieved by a single hospital intervention, and he had done it by changing what was in a basin. He did not know why it worked. Germ theory did not exist yet, and he could not name the agent he was removing. The medical establishment rejected him anyway. His appointment was not renewed. He left Vienna, published his book in 1861 to hostility and indifference, and was committed to an asylum at 47, where he was beaten by guards and died 2 weeks later, of an infected wound on his hand. That is the hole in this video's title, and it should be stated without hedging. Soap removed. It does not reliably kill. The distinction is exactly how public health describes it today. The surfactants in soap lift soil and microbes off skin, and scrubbing creates friction that lifts more, and then the rinse water carries them away. Soap does damage some organisms. It disrupts the fatty membranes of enveloped viruses and many bacteria. but the primary action is mechanical removal, not sterilization. That is enormously effective for hands, where things can be rinsed off. It is a different proposition on a cutting board that just held raw chicken, or in a hospital, or on a surface where the point is not to relocate the organism, but to destroy it. The chlorine in that Vienna basin was a store-bought chemical, and it did something no amount of homemade soap was doing, and around 10 women out of every 100 stopped dying because of it. So let us settle the account properly, because both of the loud positions on this are wrong. What the old method genuinely wins. For ordinary household cleaning, grease, food soil, floors, laundry, hands, soap and hot water and physical scrubbing does the job. And it always did. This is not a compromise position. It is the mainstream one. And there is a modern regulatory finding that makes the point sharply. Studies found no added health benefit for ordinary consumers using antibacterial soaps over plain soap and water. And in September 2016, the FDA issued a final rule removing 19 antibacterial ingredients, including triclosan, from consumer soaps on the grounds that they were no more effective than plain soap. Read that again. A federal agency examined the premium product and concluded it was not beating the basic one. For a large slice of what is sold as a cleaning necessity, the honest verdict really is unnecessary. The economics are worth stating too. A household running the old system spent essentially nothing. The ash was a byproduct of heating the house. The fat was a byproduct of eating. The sand was in the creek, and the sunlight was free. The only purchased input in the entire operation was salt, and only if you wanted a hard bar instead of a soft one. Against that, the modern equivalent is a shelf of 5 to 10 branded products, most of which contain the same handful of active ingredients in different dilutions and different colored bottles. What it does not win: disinfection, as Vienna established, hard water performance, where soap precipitates as scum and detergents do not, and the awkward one, the alkali itself. Nobody outside a demonstration is leaching lye out of a hopper. The lye in homemade soap today comes out of a bottle, produced industrially. The forgotten method has a store-bought chemical at the center of it, and now the part that actually endangers people. There is a modern movement of people cleaning without commercial products, and a portion of it operates on a rule that is not true, that natural means safe. Chlorine bleach is sodium hypochlorite. Mix it with an acid, and vinegar is an acid, and it releases chlorine gas. Mix it with ammonia, which is in many glass cleaners and in urine, and it releases chloramine gas. Both attack the eyes, nose, throat, and lungs. In high enough concentration in a small room, both can be lethal, and bathrooms are small rooms. This is not theoretical. In 2016, American poison control centers logged more than 6,300 exposures to chlorine gas, and roughly 35% of them came from mixing household cleaners. The recorded cases are ordinary. A plumber who poured a sulfuric acid drain product into a drain that already had bleach in it and left in respiratory distress. A restaurant worker who opened a dishwasher containing a mix of bleach and a lime scale remover and did not survive it. The most common version is the most innocent one. Somebody cleans a bathroom with bleach and then goes over the same surfaces with vinegar to get it extra clean, in a room with the door shut and no window open. And while we are here, one more piece of folk chemistry that does not work. Vinegar and baking soda are an acid and a base. Put them together and they neutralize each other, fizz impressively, and leave you with carbon dioxide and a weak solution of sodium acetate, essentially salt water. It is a fine, drain-fizzing party trick and a poor cleaner. Each of those two substances is genuinely useful on its own. Vinegar on scale, baking soda as a mild abrasive and odor absorber. Together they cancel, and the more vigorously they fizz, the more completely they have destroyed each other. So what is the forgotten method? In the end, it is not a product, and it was never a recipe. It is a way of thinking that the modern cleaning aisle has quietly trained out of us. That woman at the ash hopper did not own a cleaner. She owned an alkali for grease, an acid for scale, an abrasive for what was stuck, heat for what needed killing, and sunlight for what needed bleaching. And she chose between them according to what was actually wrong, because she had made all five herself and understood exactly what each one did. We buy the five as a shelf of branded bottles and mostly do not know which is which is how somebody ends up spraying two of them at the same tile and making a war gas. The chemistry has not changed since her kettle. What has been lost is not a secret ingredient. It is knowing which problem you are solving.